take limits to get us ready for something in calculus called the derivative. And the derivative has to do with tangent lines and secant lines. So first of all, you probably remember, or maybe remember, that a tangent line, you learned it in grade 9. You had a tangent on a circle in grade 9, where it touches a circle only at one point. Well, it can also touch a graph that's not a circle only at one point. And when it touches that at that point, usually it doesn't cut through the graph. There are a couple of unique situations where it touches at one point and cuts through it, but generally this would not be considered a tangent line. You're like, oh, it touches the graph only at one point. Okay, but it's cutting through the graph. Generally, the idea of a tangent is if you pick a point, it is glancing off that point right there and not cutting through, even though it might, like it does here later on, cut through the graph again at a different point over the small area that you look at. It's touching only that point, but not cutting through that point there. That's the idea of a tangent line. A secant line is just take 2 points on the graph and draw a line in between them. That is a secant line. Now, we can apply this. We can apply this to a real life situation to figure out what this is looking like. Okay? If you were driving from here to Portage la Prairie, you would leave here, you would get to Portage la Prairie an hour and a half later or an hour later. You'd look at the distance from here to Portage la Prairie. Let's make math easy. Let's say it takes us exactly an hour and it's exactly 100 kilometers from here to Portage la Prairie. If that's the case, you would have a starting point, an ending point. Here's Winnipeg, here's Portage la Prairie. You got there, but you probably didn't go the same speed the entire time. You probably didn't just drop into your car here at the school and instantaneously go 100 kilometers an hour all the way to Portage la Prairie. You would hopefully stop at red lights, not drive super fast out of the parking lot here and whip out of the corner. You would have to go slower at certain times. And so your graph might be, oh, I'm going slow at the beginning, then I'm going faster, and then slower, and stuff like that. The secant line says you started here, you ended here. It took you 1 hour to go 100 kilometers. That means your average speed was 100 kilometers per hour. Now, in order to do that, you'd probably have to be speeding somewhere along the line to make up for the stop signs and slower in the city kind of traffic. Okay? So the secant line, 1 hour, 100 kilometers. That's the secant line. That's giving your average speed that you went for the whole time. What a tangent does, and this one's really unrealistic here, but let's say that's my tangent. If I find the slope of this one, 10 minutes here, 1,000 kilometers, okay, so I was going 1,000 over 10, where this is 1/6 as far as an hour. At that moment, I was going 6,000 kilometers per hour. Really, really, really fast. The tangent line would be an instantaneous rate of change. It would be like someone phoning you while you're on the trip and saying, I just noticed your cell phone, because I've got you on tracking or whatever, I noticed it's moving really fast. Can you look at your speedometer and how fast are you going? Oh, I'm going 6,000 kilometers per hour. Thanks for phoning, I should probably stop. So that is what the difference between a tangent line and a secant line, and as far as calculus goes, we are very interested in what are the instantaneous rates of change. How fast were you going as you went through that red light on you? What exactly was your speed at that moment? So our secant line is our average rate of change. And our tangent line, its slope, will be an instantaneous rate of change. And a lot of things in math and science are really concerned about what's happening right now. How is that affecting things? What is the instantaneous rate of change? We know what's happening right now. We can predict what's going to happen coming up. Average rates of change are important too. So if we can say, what's happened over the last 10 years, how is that going to affect the next 10 years? But usually an instantaneous rate of change is a better predictor of what's going to happen next, rather than last 10 years, right? So you have been introduced to rates of change right from the beginning of grade 9. That was with lines. You learned about a slope of line. And there's your slope formula, y2 minus y1 over x2 minus x1. And we use the letter m for slope. Gradient. Oh, m for slope apparently comes from the French word for mountain. Not the English word for mountain, which also starts with m. The French word, not the Spanish word for mountain, also starts with m. I don't know. That's what I heard about. It might be a false story. Another word for slope is gradient. And have you seen this triangle before? Sometimes you see it in science. This triangle means change in y over change in x. That's what the y2 minus y1, that's your change in y, x2 minus x1, that's your change in x. And so that's your slope formula. And in calculus, we call the slope formula our first derivative. Well, our first derivative finds us the slope of a tangent line at a point. So we're going to learn that if we have a curve and we have a tangent and we want to find what the slope is of that tangent, we need to find out the change in y over the change in x. And that's what calculus is all about. It's almost, really, that's it? Yes. A lot of calculus is just about finding slopes. But what you can do with those slopes is quite powerful. So here's a random graph. And we've got distance from Winnipeg, time in hours. I don't know what we're driving here, but we're going pretty fast at some of these times. Because if this is distance in 100 kilometers, in 1 hour, we have gotten 200 kilometers away from them. We are in some sort of fancy space shuttle or something to be able to move like this. So if you wanted to calculate the average rate of change from each of these points, what you need to do is you have to figure out, as I went from 0 to 1, my change in x is 1, my change in y goes from 0 to 2, which would be 200, because this is measured in 100 kilometers. So this would be 200, and if we included the units, kilometers per hour. From 1 to 3, your x value has changed 2, and now we have gone 2 down to 1, which would be down 100 kilometers. Negative 50 kilometers per hour. Have you ever seen on your speedometer on your car the negative 50 kilometers per hour part? Does that ever show up? No. They go backwards. No, that doesn't have. What does the negative mean here? It's just talking about our direction, right? We were going very fast away from Winnipeg, and then we're like, oh, I have to go back, forgot my cell phone. And you almost get back, and then you realize, oh, it's in my pocket, right? I hate that. I don't know if it's ever happened to you, where like I leave school and I do a check. Do I have my keys? Do I have my phone? Do I have my wallet? And they tend to be in the same spot. So it's like that on my jacket, and I'm good to go. Okay? And it's happened to me that I'm phoning someone, and I'm going home, and I'm like, I should do the check. And I'm talking on the phone, and I'm like, it's not there. And I have like started looking around, and then you realize, is that it? Just me? No, okay, I'm not. All right. Okay, from 3 to 4. From 3 to 4, your change in x would be 1. You're going back up 100, so that would be 100 kilometers per hour. From 1 to 4, our change in x is 3, but we've stayed the same. 0 kilometers per hour is our average speed. We could have just stayed there and got the same amount done. And finally, from 4 to 5, again, there was no change. But from 4 to 5, can you see that we've actually stopped? We weren't moving at all. But from 1 to 4, things did happen. So our average rate of change is just that, figuring out from one time to the next, how far you've gone, and what has happened on average over those times. So all we did was calculate the slope. So where's this going? And how is this connected to limits? So here's the idea. And I actually got you to do one of these, unbeknownst to you. Some of you got to question 3A in your groups yesterday. And it was actually a derivative question that you didn't know. You just acted like a normal limit and solved it. And you've already done some derivative calculus without knowing. Here's the idea of how you can use a secant to become a tangent. So I've got a curve right here. And I've got a point A and a point B. And if I find the slope from A to B, that would be my average rate of change. That would be my slope of my secant line. And my tangent line right now is right here. And I hope that you can see that the slope of the secant line and the slope of the tangent line are different. But if I took this and I zoomed in to that section, oh, I've got my tangent at B. Doesn't matter. Here, I'll make it the same diagram. Okay. The red line is our tangent line. The blue line is our secant line. If the points B and C were closer together, can you see that the secant line is getting closer and closer and closer to the tangent line? The closer I put these 2 points together, the closer my secant line becomes my tangent line. However, I have a problem because what happens if you calculate the slope and you just use 1 point? Right? If I just take 1 point, let's go back to our notes here, let's imagine this. right? Let's say this point happens to be 1, 3. And I make another point, 1, 3. And I want to find my change in y over my change in x. My change in y is 0, my change in x is 0. I have a problem. I can't figure that out. It's not allowed. So the best I could do was to make point B as close as possible and measure that. And then what are we doing when we're doing something as close as possible? We're doing a limit. So we can change this to say, okay, what's my change in y values? Here's my y values. That would just be f of x minus f of a. What would be my change in my x values? Whatever it is there to whatever it is there. And for those of you that have taken derivatives before in the IB class, this first formula is a little bit different. It's a different form. So here we have our first formula saying that the slope from A to B is this, but if I make x get close to A, as x approaches A, the bottom will be 0. But if I can find that limit will be perfect. Perfectly the slope. And this is formula 1 for finding the slope of a tangent. So we're going to use this formula to figure out the slope of the tangent to this parabola at 2, 1. So I'll rewrite the formula out. The limit as x gets close to A, your change in y would be f of x minus f of a, and your change in x would be x minus a. In our question, what do we have? Our a value, we want to find it when the x value is 2. F of x happens to be 3x squared minus 6x plus 1 minus f of a happens to be 1 divided by x minus 2. And now this is a limit just like you've been doing before. Can we evaluate this limit? No. Why? Because we're dividing by 0. Can we do some algebra? Yes. What do I want to have happen? I want to cancel out the top with the bottom. My 1's are going to cancel. Can you see that we can factor on the top? I can take out a 3x out of these two, leaving me with x minus 2. Oh, this is working out nicely. And we have the limit as x goes to 2 of 3x. Can you evaluate that? It'll just equal 6. This 6 means the slope of the tangent at the point 2, 1 is 6. That is what this means. We took the secant formula of rise over run, we made it a limit so it got close to the tangent, and we found out that if we did it exactly on the tangent, its slope would be perfectly 6. Which is really neat because first of all, would you agree this is a parabola? 3x squared plus 6 minus 6x plus 1. It's some sort of parabola that opens up. We have a point on there 2, 1. There is only one line that perfectly makes that tangent at that point. And we just figured out that that line has a slope of 6. We figured that out because we took a secondary secant line and made that distance between the x and the a arbitrarily small. We took a limit and said, if we kept making it smaller and smaller, does it approach something? Yes. And can you see that that secant line would approach the tangent whether you came from the bottom or the top, the left side limit or the right side limit, would not matter. It would approach that same line. So we are able to draw this tangent line perfectly and know what its slope is. Relatively easy. So when we're using this formula finds specific slopes at a certain point. And so now what's the point that we're finding it at 1, 3? So we would be able to plug in that x is getting close to 1. On the bottom, it would be x minus 1. On the top, f of x is just our original equation, 4x squared minus 4x plus 3, minus f of a. F of a is just your y coordinate, right? This technically, in our example, would be f of 1. And you could plug 1 into the equation and figure it out. But I hope, since they gave you the point, you already see they figured that out for you. Saves you some time. The y value is already given to be 3 when x is 1. And again, something nice happens. The 3's cancel out. I can factor what's left. I could take a 4x out, leaving me with x minus 1. I have an x minus 1 on the bottom. Those will simplify. I can now plug in 1 and evaluate that limit. So we can say, as a statement, we can say that the slope of the tangent at the point 1, 3 is 4.